Alright, hello everybody. This video is going over 5.3, which is concentration changes over time for the AP Chemistry curriculum. The understanding is that some reactions will happen quickly while others will happen more slowly, and that will depend on concentrations and temperature. The objective for this lesson is to identify the rate law expression of a chemical reaction using data that shows how the concentrations of reaction species change over time. And then if you'd like to pause to read the essential knowledge. Graphing concentration. So when we're graphing the concentration of a reactant versus the time, it allows us to deduce the reaction order because each order is going to produce a predictable curve on the graph. So as you can see here, everything that will be in the 0th order will produce a linear line. So this will be our 0th order. The slope of that 0 order reaction is going to be equal to negative k. So slope is equal to negative k, and that's something to keep in mind for this unit. Now you can see the next one is going to be our 1st order reaction. So this would be labeled our 1st order. And then the line all the way to the left is going to be our 2nd order. And in AP Chemistry, we're really just focusing on that 0, 1, and 2 order. So this is just a very helpful figure if you want to pause and kind of run through everything. The first item is the differential rate law, which we are going to talk a little bit more about this lesson. The next is concentration versus time, which is what we just went over. Again, you can see the 0th order is going to be a straight linear line with a negative slope. And then our 1st order is going to have a little bit more curve, and then our 2nd order is going to have a lot more curve. Then we have our integrative rate law. Again, we're going to talk about that today. And then next I want to briefly go over this straight line plot to determine rate constant. We're going to go in more detail in the next coming slides, but this is a very nice summary of these plots to determine the rate constant. So if you are ever struggling with some kind of worksheet or homework or even our prep books, please have this open because I believe that this slide is very helpful. All right, so let's go in a little bit more detail about these line plots and how we can use them to solve for rate law. So when we are using 0 order reactions in a graph like this, we're always going to have the concentration of A, which is just one of the reactants, and on the x-axis we're going to have T for time. Now remember that this slope is equal to negative k, and it's very important that you know that our initial reading or our initial concentration is going to look like the concentration of A with a subscript of 0, and that just means that there's no time. So it's the very first concentration reading. So when we are talking about how to solve for the rate law, we're going to use y equals mx plus b. So we know our y value is the concentration of A. We know our slope is negative k. We know our x value is time. And our b is what we are starting out with, which is the very first concentration reading for time. So when you are solving for k, I need you to keep in mind that for 0 order, k units will always be molarity divided by time. Now normally it's in seconds, but keep in mind this could also be molarity over years, it could be molarity over minutes, it could be any unit of time in the denominator. Okay, so now we go on to 1st order. So some things are the same, some things have changed. So we still have a negative line, which means our slope is still going to be negative k. Now if you look at our y value, that is changing. instead of just the concentration of A, it's going to be the natural log of A, of the concentration of A, and then we still have units of time for the X value. Now, when we were talking about the initial reading, this is going to be the same concept with the natural log. So we have the natural log of the concentration of A for time 0. So that would be our initial concentration. And so when we are solving for the rate law, or K, we can plug this into y equals mx plus b. Our y value is the natural log of the concentration of A. Our slope is negative k. Our x is time. And our b is the natural log of A at 0 time. Now, keep in mind, this is the next thing I need you to remember, is that for K, when we're in first order, the unit is always going to be time to the negative first power, or 1 over time. So this can be written as s to the negative first, or it can be written as 1 over s. This could also be minutes to the negative first power, or 1 over minutes, and you can even use something like years or hours or days. Any unit of time, it just depends on what it gives you. All right, and then finally, second order. This one's easier to remember because it is the only one with a positive slope. So our slope for second order is going to be equal to positive k. Now for our y value, since again it is inverted, we are now going to have 1 over the concentration of A, and we're still going to have time as our x value. And then our initial concentration is going to be 1 over the concentration of A at 0 time. So when we are plugging this into our y equals mx plus b in order to solve for k, we're going to have 1 over the concentration of A for our y value. We're going to have a positive k for our slope. We're going to have time for our x value. And then we're going to have 1 over the concentration of A to 0 time for our B. So this would be how you would solve for K, plugging in those values. And then just keep in mind, when you have second order, the unit for K is always going to be. Okay, so now let's go over half-life. So you should have briefly touched on this in your previous chem class, but we're just going to go over it a little bit more. So for half-life, the first order, which is the main one we're going to talk about in regards to half-life, is constant. So half-life is constant when your reaction is in first order of kinetics. So it is important to remember that when you are solving for half-life, it is always 0.693 divided by K, and that will give you your half-life. So on this graph, it's just a visual representation. When you have K, a higher initial concentration has no impact on the time needed for half of the reactant to be consumed. For first order reactions, the half-life does not depend on the initial quantity. A lower initial concentration has no impact on the time needed for that half to be consumed. Using the data provided, determine the reaction order and then calculate the value for K with units. So you could figure this out if you wanted to by graphing the points. So we're given our X values and our Y values with time versus concentration. And if you plot your X and your Y on a graph and it forms a straight line with a negative slope, that means you're going to have a 0 order reactant. Now, if that is not a straight line, you could then go ahead and take the natural log of each of these numbers. And if you plotted the natural log of the concentration versus time and that was a straight line, that would mean that the reaction order is 1. Now, if that was still not a straight line, you can automatically assume that it is going to be second order just because AP Chemistry only does 0, 1, and 2. But if you did not want to plot those, you could also do it with math. So if I look at the concentration values, they are not decreasing with the same amount of concentration. I wrote it up here so I didn't get in the way of our next step. But you can see when we go from a concentration of 1.25 to 0.9122, our change is 0.3378. But then when we go from 0.9122 to 0.6657, our change is 0.265. So that is not an equal change over time. So we are going to move on to the natural log of these numbers and see if that gives us a natural change over time. So when we are looking at the natural log of these, let's just do the first couple to make sure that they are changing in the same amount of concentration for each one. So when we get the natural log of 1.250, we get 0.223. The natural log of 0.9122 is going to be negative 0.092, and then negative 0.407, and let's just do one more, 0.722. So now let's look at the change between the natural log of all these concentrations. When we go from 0 minutes to 100 minutes, the change in concentration is going to be 0.315. Then when we go from 100 minutes to 200 minutes, again, it's 0.315. And then when we go from 200 to 300 minutes, again, it's 0.315. So this is telling us that the change in concentration when we take the natural log of it is the same for each change in time. That's going to tell us that this is first order because the natural log was where our time or our concentration change was constant. So this is going to tell us that it is in first order. So then we need to calculate A. So when we have a first order reaction, we know that the rate is equal to K with the concentration of A, and since this is first order, it's going to have a 1 or nothing there. So when we are using first order, if we go back to determining the rate, we're going to use y equals mx plus b, but since it's first order, it's going to be the natural log of the concentration of A equals our negative k for slope, our t for x, and our b value, which is the natural log of the concentration of A at no time. So we calculated our natural log of concentration we're going to use for 100 minutes, and we calculated the natural log already to be negative 0.092, so we're going to use that value. That's going to equal our negative k, which is what we are solving for, and we are using 100 minutes for time. So keep in mind you could have used something else. You could have used this negative 0.407 with 200 minutes, but I just chose the 100-minute value. So then we have our B value, which is the natural log of the initial concentration, and that is going to be our 0.223. So when we do that, we're going to get a K value of 3.15 times 10 to the negative 3. And remember, for first order, our K units are always going to be time to the negative first power. In this case, we have minutes, so our unit is minutes to the negative first power, and that is our answer. Okay, and then our last example for this lesson is about half-life. So a first order reaction has 1/16 of the original amount left after 500 seconds. What is the half-life of the reactant in this reaction? So let's just do very simple numbers. Let's say we started out with 100 grams, and we know that 1/16 of 100 grams is going to be 6.25 grams. And again, you could just take 100 and divide it by 16, and it's 6.25. So we need to figure out how many times it takes to get to 6.25. So it is called half-life, so it's going to break in half every single time. So the first one would break in half to 50 grams, then to 25 grams, then to 12.5 grams, and then to 6.25 grams. So just with basic understanding of half-life, we could just kind of figure this out. So it took 1, 2, 3, 4 times, and we know that it is out of 500 seconds. So if we divide that by 4, because it took us 4 times to get to 6.25, that means that our half-life is 125 seconds. Now, you could do it based on logic like we just did, or you could do it with math as well. So we know that this is a first order reaction, which means the half-life is constant. So every single time you take your reactant and you divide it in half, it's going to be the exact same amount of time for every single half-life. So we can also use the first order y equals mx plus b in order to solve for the k value. And then remember, half-life is equal to 0.693 over k. So once we solve for that rate law, we can plug it into that in order to solve for our half-life. So we know it's first order, so it's going to be the natural log of the concentration at any time equals negative k times time plus our natural log of concentration at 0 time. So we are looking at the ending amount of reactant. So we're going to take the natural log of 6.25, and then we are solving for k, and our time is 500 seconds. And then our initial is going to be 100. So we're starting with 100. Okay, so we were trying to find the half-life at 6.25, so that's what we were putting in for our y value. At 6.25, we know it's at 500 seconds. And then for our very initial amount, we know that we're starting with 100 grams, so we plug that into B. So when we do that, we end up getting K is equal to 0.00555. And for first order, remember, it's time to the negative first power. Here we have seconds to the negative first power. So now we can take this equation down here, 0.693, and divide it by 0.00555, and it's going to give you 125 seconds. So you can do this either with logic, which we did on the left side, or you can do this with math, which we did on the right side. Either way works, you're going to get the exact same number.